At 2:46 on a Friday afternoon, Japan's machines did almost exactly what they had been built to do. Earthquake sensors reacted. Warnings appeared. Trains began to slow. Factory lines stopped. At nuclear power stations along the coast, operating reactors shut down automatically. Then the shaking kept going. People who had lived with earthquakes all their lives noticed the difference. This was not one hard jolt followed by silence. Buildings rolled and swayed. Ceiling panels fell. Roads cracked. Power disappeared across parts of northeastern Japan. In offices hundreds of kilometers from the epicenter, workers held desks and watched towers move. Along the Pacific coast, the shaking created a second question that mattered even more than the first. What was the ocean about to do? Within roughly 3 minutes, the Japan Meteorological Agency issued its first major tsunami warnings. That was fast. The problem was the first rapid estimate of the earthquake's size. It was too small. A giant offshore rupture was still unfolding, and the warning system had not yet understood just how much of the seafloor had moved. The ocean was already moving. Less than an hour after the earthquake began, seawater was crossing seawalls, roads, farms, neighborhoods, ports, and an airport. In narrow bays, it climbed to extraordinary heights. On flat plains, it traveled kilometers inland. Cars floated beside houses. Fishing boats appeared in streets. Entire neighborhoods were turned into moving fields of wood, metal, mud, fuel, and water. And on the Fukushima coast, the same tsunami was heading toward a nuclear power station where the reactors had already shut down safely. That detail is the key to the whole story. Fukushima Daiichi did not begin with a reactor refusing to stop. The reactors stopped. The crisis came afterward, when the tsunami destroyed electrical systems and crippled the equipment needed to keep removing heat from nuclear fuel that remained hot even after shutdown. So March 11th was not one disaster. It was a chain. A massive fault rupture moved the seafloor. The moving seafloor displaced the ocean. The tsunami destroyed towns and critical infrastructure. At Fukushima, the loss of power and cooling turned a natural disaster into a nuclear emergency. Over the next 100 facts, we are going to follow that chain in the order it actually happened. Some of the strangest parts are not the famous images. They are the small timing differences. A helicopter that escaped an airport only minutes before the water arrived. A warning that was fast but too low. A town that had prepared for tsunamis for generations and was still overwhelmed. And a nuclear station that survived conditions another station nearby did not. The first fact begins before anyone had seen the wave. Fact number 1. The disaster began in the middle of an ordinary Friday afternoon. The main earthquake struck at about 2:46 in the afternoon, Japan time, on March 11th, 2011. That timing matters because millions of people were awake, at work, in school, shopping, driving, or traveling. Offices were full. Factories were running. Children were still at school. Trains were moving through Japan's highly developed rail network. This was not a disaster that arrived in darkness while most people slept. It happened in full daylight, with cameras running and newsrooms staffed. Full daylight and working cameras are part of the reason the event was recorded from so many angles. In Tokyo, far from the worst tsunami damage, tall buildings swayed and office workers moved into streets and open spaces. In the northeast, the shaking was much stronger. Objects fell, roads cracked, power failed. Along the coast, people had to make a second decision almost immediately. Surviving the shaking was not enough. They had to think about the ocean. The date would soon become known simply as 3/11 in Japan. But at 2:46, nobody knew that yet. It was still a normal afternoon that had just become a very large earthquake. And within seconds, a system built to buy people a little time began reacting. Fact number 2. Japan's earthquake early warning system sent alerts before the strongest shaking reached many places. Japan had already built one of the world's most advanced earthquake early warning networks. The basic idea is simple. An earthquake sends out different kinds of seismic waves. The first waves move faster and are usually less damaging. Sensors detect those early waves, computers estimate what may be coming, and warnings can reach people and machines before the stronger motion arrives. For this earthquake, the Japan Meteorological Agency says an emergency warning was issued about 8.6 seconds after the first wave was detected at the nearest seismic station. 8.6 seconds does not sound like much. For a person, it may be only enough time to step away from a window or get under a desk. For a machine, it can be valuable. Automatic systems can slow trains, stop elevators at safe floors, shut industrial equipment, and warn hospitals or control rooms. The warning did not prevent the disaster. No warning system can stop the ground from moving. But it is an important part of the story because it shows how prepared Japan already was for earthquakes. The failure on March 11th was not that Japan knew nothing about seismic danger. The problem was that the event grew beyond some of the assumptions built into systems designed from earlier experience. The earthquake itself was the first sign of that scale. Fact number 3. It was the largest earthquake ever recorded in Japan by modern instruments. The Japan Meteorological Agency gives the earthquake a magnitude of 9.0. The United States Geological Survey later listed it as magnitude 9.1, using its preferred calculation. Those numbers are close enough that the main point does not change. This was a truly enormous earthquake. Japan had experienced deadly earthquakes before. The Kobe earthquake in 1995 had killed thousands. The country had strict building codes, drills, emergency plans, and a population familiar with shaking. But a magnitude 9 event belongs to a different class. Magnitude is not a simple scale where 9 is only a little stronger than 8. Each whole step represents a huge increase in the energy released. A magnitude 9 earthquake therefore belongs to a different class from the earthquakes people regularly feel in Japan. It was powerful enough to be felt across much of the country. The strongest official Japanese seismic intensity, level 7, was recorded in Kurihara City in Miyagi Prefecture. Strong shaking was recorded across a wide area of northeastern and eastern Japan. For years afterward, people would naturally focus on the tsunami, because that is what caused most of the visible destruction and most of the deaths. But the wave only existed because something extraordinary had happened under the ocean. And the earthquake did not come from a tiny point beneath the sea. Fact number 4. The rupture was hundreds of kilometers long. Maps often show an earthquake with a single dot called the epicenter. The dot is useful for orientation, but it can give the wrong picture of a giant event. A magnitude 9 earthquake is not one little underground snap at one location. On March 11th, a huge section of the boundary between tectonic plates ruptured. Japanese analysis estimated a fault area roughly 450 kilometers long and around 200 kilometers wide in one model. The United States Geological Survey described a rupture region roughly 400 kilometers long and about 150 kilometers wide. The exact dimensions vary with the scientific model, but either way, the scale is enormous. Imagine a break stretching along a large portion of a country's coastline rather than a single crack under one town. That helps explain another feature of the disaster. The shaking lasted a long time because the rupture itself took time to spread. Different parts of the fault were moving in sequence. The Japan Meteorological Agency estimated that the main rupture process lasted around 3 minutes, with several major bursts of movement. For people on land, those minutes felt very different from the short jolt many associate with an earthquake. The ground moved, eased, and moved again. Under the ocean, the movement was even more important. That is the scale required to understand everything that came next. Fact number 5. Parts of the fault moved by tens of meters. When scientists reconstructed the earthquake, they found that the plates had not shifted by a few centimeters. In some areas, the movement was measured in tens of meters. The Japan Meteorological Agency estimated maximum slip in one analysis at roughly 20 to 30 meters. Later, United States Geological Survey modeling found that the fault may have moved as much as 50 to 60 meters in the area of greatest slip near the Japan Trench. Those estimates come from different methods, so they should not be treated as contradictory headlines. They are attempts to describe a rupture that happened deep offshore across an enormous area. The important part is simple. The seafloor moved violently and over a huge distance. A tsunami can begin exactly this way. Water does not need a storm. It does not need wind. If a large area of the ocean floor suddenly rises or falls, the water above it is displaced. Gravity then tries to restore the surface, and that disturbance races outward. The size of the earthquake therefore mattered enormously. A smaller offshore quake may produce little or no dangerous tsunami. This one moved enough of the seafloor to set an enormous volume of water in motion. But there had been a warning sign 2 days earlier. Fact number 6. A magnitude 7.3 earthquake struck near the future rupture area 2 days before the main shock. On March 9th, 2 days before the disaster, a strong earthquake occurred off Sanriku in the same broad region. The Japan Meteorological Agency gives its magnitude as 7.3. It was strong enough to trigger a tsunami advisory and was followed by a busy sequence of earthquakes. After March 11th, that earlier event became easy to see as a foreshock. Before March 11th, nobody could know that with certainty. The word foreshock only makes sense after a larger earthquake follows. Until then, it is simply an earthquake in an active seismic zone. That is an important distinction because disasters often look much easier to predict when we already know the ending. The March 9th event showed that the plate boundary was active, but it did not provide a reliable countdown to a magnitude 9 earthquake. Japan had no practical warning, saying that the largest earthquake in its recorded history would begin about 48 hours later. When the main rupture finally started at 2:46 on Friday afternoon, it began roughly 130 kilometers east-southeast of the Oshika Peninsula. The epicenter was offshore, but the movement was so large that the effects were measured not just in shaking. Parts of northeastern Japan permanently changed position. Fact number 7. Part of northeastern Japan moved more than 5 meters during the earthquake. The Geospatial Information Authority of Japan operates a dense network of satellite positioning stations. After the earthquake, data from the Oshika Peninsula showed a remarkable change. One observation point had moved about 5.3 meters toward the east-southeast and dropped by around 1.2 meters. 5.3 meters is not a vibration. It is a permanent change in position. The land did not simply shake and return to exactly where it had been before. The movement was large enough that Japan had to revise official survey coordinates over a wide area. Control points used for mapping and construction could no longer be assumed to have the same positions they held before the earthquake. Japan eventually introduced an updated geodetic datum to account for the crustal deformation. Put another way, the earthquake shifted the ground beneath ordinary roads, bridges, property lines, and survey markers. And the change did not stop at horizontal movement. Some coastal areas also sank, making them more vulnerable to flooding and later high tides. For surveyors, mapmakers, engineers, and coastal planners, the ground itself had to be treated as newly moved. Fact number 8. The earthquake slightly shortened the length of a day on Earth. Scientists at the National Aeronautics and Space Administration calculated that the redistribution of mass caused by the earthquake should have made Earth rotate a little faster. The estimated change was tiny, about 1.8 microseconds shorter per day. A microsecond is 1/1,000,000th of a second, so nobody could notice this without extremely precise instruments and calculations. The same research estimated that the earthquake shifted Earth's figure axis by roughly 17 centimeters. This does not mean the geographic North Pole suddenly jumped across the map. The figure axis describes how the planet's mass is balanced as it rotates. These numbers are often repeated because they sound dramatic, but they are useful only if we keep the scale honest. The changes were physically real, yet far too small to affect daily life. What they do show is that a magnitude 9 earthquake involves the movement of so much mass that its effects can be discussed not only in terms of broken roads and waves, but also in terms of the rotation of the planet. Fact number 9. The main rupture lasted for roughly 3 minutes. For many people, an earthquake is remembered as a sudden jolt followed by a few seconds of shaking. March 11th was different. The Japan Meteorological Agency's analysis found that the main rupture process continued for around 3 minutes. It involved several major episodes of rupture rather than one instant release. That long duration mattered psychologically and physically. During a prolonged earthquake, people have time to realize that what they are feeling is not normal. Buildings continue to move, ceiling panels fall, cabinets empty, water sloshes from tanks. Roads and embankments are stressed again and again. In high-rise buildings farther away, long-period motion caused some structures to sway for an extended time. In northeastern Japan, the shaking was far more violent. The duration also mattered, because every extra second of rupture was part of the process generating the tsunami. By the time the ground stopped moving, the ocean had already been disturbed across a huge region. People near the coast did not have the luxury of treating the end of the shaking as the end of the emergency. They needed to move away from the sea. And only a few minutes after the earthquake began, the first tsunami warnings were already being issued. Fact number 10. Japan issued tsunami warnings about 3 minutes after the earthquake. At 2:49 in the afternoon, only about 3 minutes after the earthquake began, the Japan Meteorological Agency issued tsunami warnings and advisories for large sections of the coast. 3 minutes is remarkably fast. The agency had to detect the earthquake, estimate its location and magnitude, compare the event with tsunami models, and send warnings while the country was still shaking. The first warnings included major tsunami warnings for the most threatened areas. Over the following minutes and hours, the warnings were expanded and upgraded as more information arrived. This rapid response saved lives. Many people began evacuating as soon as they felt the long, strong shaking or heard warnings. But there was a serious problem hidden inside the first calculation. The earthquake was so large that the early system underestimated its magnitude. Some seismic instruments were effectively overwhelmed by the strength of the signals, and the initial magnitude estimate did not fully capture the size of the rupture. That led to tsunami height estimates that were too low in some places. The lesson is crucial. A warning can arrive quickly and still communicate the wrong scale. Fact number 11. The first tsunami height estimates were dangerously lower than what actually arrived. In the first minutes after the earthquake, the Japan Meteorological Agency's magnitude estimate was too small. That affected the first tsunami forecasts. Later reviews by the agency found that early information, such as a predicted tsunami height of around 3 meters in some areas and reports of small first observed waves, could have given some people a false sense of how severe the danger was. The actual tsunami was far larger along parts of the Tohoku coast. Official tide observations later showed more than 9 meters at Soma before the record became incomplete, more than 8 meters at Miyako and Ofunado, and field surveys found run-up heights far higher still. Experts were not sitting idle. The warning went out in minutes. The problem was that the event exceeded the assumptions of the first estimate. After the disaster, Japan changed the system. When an earthquake is so large that its true magnitude cannot be calculated reliably in the first moments, the agency can now avoid giving a deceptively precise low number and use stronger qualitative language indicating a huge tsunami. Fact number 12. A tsunami in deep water can be hard to notice even while it is moving incredibly fast. Far from shore, a tsunami is not necessarily a towering wall of water. Its wavelength can be enormous, and its height in the open ocean may be relatively modest compared with what happens at the coast. The dangerous part is the amount of water involved and the speed at which the energy travels. In deep ocean water, tsunami waves can move at speeds comparable to a jet aircraft. As the wave reaches shallower water near land, it slows. The energy has fewer places to go vertically and horizontally, so the water can build in height and push inland. Coastline shape matters too. Bays, Narrow inlets, river mouths, slopes, and underwater topography can concentrate or redirect the flow. Two communities separated by a relatively short distance can therefore experience very different water heights. The 2011 tsunami was not one uniform blue wall striking the entire coast at exactly the same height. It was a changing, turbulent flood, shaped by the ocean floor and the land it encountered. Fact number 13. A deep ocean tsunami buoy recorded the wave about 25 minutes after the earthquake. The United States National Oceanic and Atmospheric Administration operates deep ocean instruments designed to detect tsunamis through changes in water pressure. About 25 minutes after the earthquake, one of these deep ocean systems recorded the tsunami. That kind of observation is extremely valuable because it helps scientists confirm that a dangerous wave has actually been generated and improve forecasts while the tsunami is still crossing the ocean. For Japan's nearby coast, however, 25 minutes was already a large fraction of the available evacuation time. In some areas, the first dangerous water arrived within roughly half an hour. Other areas had somewhat longer. That difference is why coastal earthquake safety in Japan emphasizes a simple rule. If you feel strong or long shaking near the sea, do not wait for perfect information. Move to higher ground. The people closest to the source cannot depend on a distant buoy to tell them what the ground has already told them. The farther the tsunami traveled, though, the more time warning centers had to act. And the wave did not stop at Japan. Fact number 14. The tsunami crossed the entire Pacific Ocean. Once generated, the tsunami radiated outward from Japan. The National Oceanic and Atmospheric Administration modeled and measured the wave as it traveled across the Pacific. It reached Hawaii after roughly 8 hours and the west coast of the United States after around 9.5 hours. Over the following hours, it continued across the ocean basin, reaching coastlines thousands of kilometers from Japan. Warnings were issued around the Pacific. Harbors were cleared where possible. People were moved away from vulnerable shorelines. The damage outside Japan was far smaller than the devastation in Tohoku, but the wave was still powerful enough to damage harbors in California and cause losses in places such as Hawaii and Chile. One of the strangest later observations was that the tsunami was linked to ice shelf calving in Antarctica. That global reach is easy to miss when watching footage of one Japanese town. The earthquake happened off Honshu, but the ocean carried its energy across an entire basin. Near the Japanese coast, there was almost no such distance to soften the surprise. For people on the coast, there was no need to understand the physics first. The only useful response was to get higher. Fact number 15. Along parts of the coast, the tsunami reached land within about half an hour. The exact arrival time varied by location, but the first tsunami waves reached sections of northeastern Japan roughly 10 to 30 minutes after the earthquake, while other places were struck somewhat later. Half an hour is a brutally short window when the earthquake itself has lasted for minutes. Roads are damaged, traffic is building, power is failing, elderly relatives need help, and people are trying to decide which warning to trust. A perfect evacuation plan on paper becomes much harder when the roads are shaking and everyone tries to move at the same time. Some people evacuated on foot, others used cars. Cars could help people who needed to travel farther or assist relatives, but traffic jams also became deadly traps in some low-lying areas. Many schools and communities had practiced evacuation. In places where people moved immediately to higher ground, those habits saved lives. In other locations, delay, uncertainty, underestimated wave forecasts, or simply the extraordinary reach of the water proved disastrous. The figure is memorable because it shows why a tsunami cannot be described by one single height for an entire coastline. Fact number 16. In one location, the tsunami run-up climbed to more than 39 meters above sea level. Run-up is not exactly the same thing as the height of a wave at the shoreline. It describes how high the water reaches as it moves onto land or up a slope. Post-disaster surveys found a run-up of more than 39 meters in the Miyako area of Iwate Prefecture. That is roughly the height of a building with many stories. The National Oceanic and Atmospheric Administration also reported confirmed run-up values around 40 meters in parts of Japan. This does not mean a perfectly shaped 40-meter wall of water marched along the entire coast. The extreme values occurred where local geography amplified the flow and allowed water to climb high terrain. Still, it shows why historical experience and ordinary coastal defenses were not enough everywhere. A community might have a seawall designed for a severe tsunami and still face water that overtopped it. Japan's northeast coast had a long history of tsunamis, including destructive events in 1896 and 1933. People had built walls, evacuation routes, and monuments because the danger was known. Fact number 17. Some tsunami gauges stopped recording because the tsunami damaged the instruments themselves. When scientists later tried to determine the maximum water height at several coastal stations, they found an unusual problem. Some instruments had been damaged or destroyed before the largest part of the tsunami could be measured. At Miyako, recovered records showed at least 8.5 meters. At Ofunato, at least 8 meters. At Soma, at least 9.3 meters. At Ishinomi's Ayukawa station, the recovered record showed at least 7.6 meters. The phrase "at least" matters. The equipment failed or the record became incomplete, so the true maximum could have been higher. The damaged gauges reveal the scale in a different way. The instruments built to measure the sea were themselves overwhelmed by the sea. Later, teams walked the damaged coast looking for physical evidence. Watermarks on buildings, debris caught high above the ground, stripped vegetation, and other traces that showed where the water had reached. Those field surveys helped create a much fuller map of the tsunami than the surviving gauges alone could provide. Fact number 18. Narrow bays could make the water rise higher. The Sanriku coast in northeastern Japan is famous for its complicated shape, with steep terrain and narrow bays cutting into the land. That coastline is beautiful, but it can be dangerous during a tsunami. As water is funneled into a narrowing bay, the wave can become higher and more destructive. The shape of the sea floor and coast can concentrate energy instead of spreading it out. This helps explain why places in Iwate Prefecture recorded some of the highest run-up values. It also explains why a simple statement such as the tsunami was 10 meters high can be misleading. In one harbor, the water may rise several meters. A short distance away, in a narrow inlet or on a slope, it may climb much higher. For emergency planning, that means historical local evidence matters. A tsunami stone on a hillside, an old flood line, or a record from a previous disaster can contain information that a national average cannot. But the 2011 tsunami also moved far across flat land, where there were no narrow valleys to amplify it. The Sendai Plain showed a different kind of danger. Fact number 19. On flat coastal plains, the tsunami traveled several kilometers inland. Around Sendai, the landscape near the coast is much flatter than the steep Sanriku shoreline farther north. There, the problem was not an extreme run-up climbing a mountain slope. It was the ability of a huge volume of water to keep moving across low ground. Satellite images and field surveys showed broad areas of the Sendai Plain covered by seawater and debris. Farms, roads, neighborhoods, and industrial areas were flooded. In some locations, the water traveled several kilometers inland. That kind of flooding changes how people must think about evacuation. Moving a few blocks away from the beach may not be enough. If the land remains low, the safest direction may be upward rather than simply inland. The flat plain also contained Sendai Airport, a major transportation hub for the region. After the earthquake, an emergency rescue helicopter managed to take off from the airport. 37 minutes after the quake, it was in the air gathering information. Only a few minutes later, the airport itself was being swallowed by the tsunami. Fact number 20. Sendai Airport went from emergency base to disaster scene in less than an hour. Sendai Airport sat on the coastal plain close to the Pacific. After the earthquake, an emergency rescue helicopter known as Michinoku was scrambled to survey the damage. The Ministry of Land, Infrastructure, Transport, and Tourism says the helicopter took off 37 minutes after the earthquake. A few minutes later, the airport was engulfed by the tsunami. Television footage showed water carrying vehicles and debris across the airfield. The first floor of airport facilities was heavily damaged, and water flooded parts of the terminal. People inside moved to upper levels for safety. The image is striking because airports are usually symbols of connection. They move people and supplies quickly. In a disaster, they can become vital lifelines. On March 11th, Sendai Airport was suddenly cut off by the same water that was destroying nearby communities. Yet the airport would later become one of the clearest examples of rapid recovery. Massive pumping operations removed floodwater. Military and civilian crews cleared debris. Special flights returned within weeks. An airport that had been under seawater would soon become one of the region's most useful lifelines. Fact number 21. The tsunami did not arrive as one clean wave and then disappear. A dangerous misconception is that a tsunami has a single main wave. In reality, a tsunami is a series of waves and long surges. Water can arrive, pull back, and return again. Later waves can be larger than the first. That matters because people naturally want to go back. They want to check a house, find a relative, photograph damage, or see whether the danger has passed. On March 11th, the Japan Meteorological Agency kept tsunami warnings and advisories active for many hours. Some were not completely lifted until the afternoon of March 13th. The sea did not return to normal when the first water receded. Harbors kept surging. Currents remained dangerous. Debris moved back and forth. Even after the most destructive inland flow had ended, the coast could not simply reopen. This also explains why early observations of a small first wave were dangerous to communicate without strong context. A first wave of only a few tens of centimeters did not mean the tsunami would stay small. After 2011, Japanese warning language was changed, partly to reduce that kind of false reassurance. Fact number 22. Seawalls that had protected communities from earlier tsunamis were overtopped. Northern Japan had spent decades building coastal defenses. Some towns had high concrete seawalls, floodgates, and breakwaters. These structures were not decorative. They were built because the region had a long memory of destructive tsunamis. In many places, the defenses helped. They reduced smaller waves, delayed flooding, or gave people additional time. But on March 11th, the tsunami exceeded the design assumptions of many structures. Water poured over walls. In some places, walls were damaged or destroyed. Once a large volume of water crossed a defense, the land behind it could flood quickly. The lesson is not that seawalls are useless. That would be too simple. A wall can reduce risk without eliminating risk. The problem comes when a physical barrier becomes a psychological promise. If people believe a wall makes evacuation unnecessary, the wall can indirectly create a new danger when an extreme event exceeds it. Japan's reconstruction after the disaster tried to combine several layers of protection: stronger coastal structures, higher evacuation routes, better warnings, relocation of homes, and education that assumes defenses can fail. Fact number 23. The town of Taro had become famous for fighting tsunamis long before 2011. Taro, in Iwate Prefecture, had been struck by devastating tsunamis in the past. Over decades, the community built an enormous system of seawalls and became known in Japan as a town that took tsunami protection seriously. That history makes what happened in 2011 especially important. The town did not ignore the danger. It had invested in protection because older disasters were still part of local memory. Yet the March 11th tsunami overtopped defenses and caused severe destruction. The story of Taro is useful because it cuts through an easy explanation. It is tempting to look at a disaster and say people should simply have prepared better. Taro had prepared. The scale of the event still exceeded parts of the system. Afterward, the exposed remains of damaged structures became part of the region's disaster memory. The question changed from how to stop every tsunami to how to survive even when the largest barrier is exceeded. Taro became evidence that preparation can reduce risk without ever making an extreme event harmless. Fact number 24. Rikuzen Takata lost a coastal forest of about 70,000 pine trees, but one tree remained. Before the disaster, Takata Matsubara was a famous grove of roughly 70,000 pine trees along the coast of Rikuzen Takata in Iwate Prefecture. The tsunami tore through the area. The grove was almost completely destroyed. Only one tall pine remained standing in the devastated landscape. It became known as the Miracle Pine. The tree was around 173 years old and more than 27 meters tall. It did not survive permanently. Salt damage eventually killed it, but the trunk was preserved and reconstructed as a memorial. The reason the image became so powerful is easy to understand even without knowing the local history. A single tree standing where tens of thousands had disappeared gave the scale of the water a visible reference point. Rikuzen Takata itself suffered catastrophic damage. Official reconstruction material describes tsunami heights in the city reaching more than 18 meters. Years later, the area around the preserved tree became part of a memorial park. The landscape was rebuilt, but the tree was intentionally kept as a marker of what had happened. Farther south, the tsunami was moving into cities where the danger did not end when the water stopped rising. Fact number 25. In Kesennuma, the tsunami was followed by major fires. Kesennuma is a fishing city in Miyagi Prefecture built around a harbor and industries connected to the sea. When the tsunami entered the city, it carried boats, vehicles, timber, fuel, and pieces of buildings through flooded streets and industrial areas. Fires broke out in the damaged city and burned through parts of the night. That combination is one reason tsunami disasters can become more complicated than flooding alone. Water destroys electrical systems and moves fuel containers. Roads become blocked. Firefighters may be unable to reach burning areas because the same water that caused the fire has cut off access. In Kesennuma, images of flames reflecting across dark floodwater became some of the most disturbing scenes from the first night. The city was also an important fishing center, so damage to the harbor and processing industry affected livelihoods long after rescue operations ended. Rebuilding a coastal community, therefore, meant more than replacing houses. Fishing ports, cold storage, roads, factories, markets, and boats all had to return if the town was going to function again. Fact number 26. The disaster did not destroy one town. It damaged a vast stretch of Japan's Pacific coastline. When people remember March 11th, they often remember one famous video clip: water crossing a road, a building floating away, or a wave reaching an airport. But the disaster area was enormous. Iwate, Miyagi, and Fukushima prefectures suffered the worst losses, while damage extended into other parts of northeastern and eastern Japan. The National Oceanic and Atmospheric Administration reported that roughly 2,000 kilometers of Japan's Pacific coast were affected by the tsunami in some way. This scale created a rescue problem that no single city could solve. Fire departments, hospitals, police stations, local government offices, fuel depots, roads, and communication systems could all be damaged at the same time. A nearby town that would normally send help might be dealing with its own emergency. National agencies therefore had to think regionally. Roads needed to be cleared not just to reconnect one neighborhood, but to open corridors into an entire coastline. The Japanese self-defense forces would eventually carry out the largest disaster relief operation in their history. Fact number 27. Strong shaking itself was a tsunami warning for people near the coast. In a coastal earthquake zone, a crucial warning may come from the ground itself rather than a screen or siren. It is physical. If the ground shakes hard enough that standing becomes difficult, or if the shaking continues for an unusually long time, people near the sea are taught to move to high ground even before an official message arrives. On March 11th, that rule saved lives. Some people began evacuating immediately because the earthquake felt far too large to ignore. The official warning system added information, but it could never give every coastal resident the same amount of time. A person near the source might have only minutes. A person farther away might have much longer. Modern Japanese tsunami education therefore emphasizes independent action. Do not wait for a neighbor to decide. Do not wait to see the water. Do not assume the first announced height is the final answer. The most dangerous moment can be the moment when nothing dramatic is visible yet. The shaking has stopped, the sky looks normal, the ocean may even appear calm. Then the water begins to change. Fact number 28. The sea does not always pull back before a tsunami arrives. A famous warning sign of a tsunami is a sudden retreat of the ocean, exposing seafloor that is normally underwater. That can happen, and when it does, it is an unmistakable reason to run inland and uphill. But it is not guaranteed. A tsunami can begin with a rising surge instead. Whether the first movement is a drawdown or a push depends on the shape of the wave and local conditions. Waiting for the sea to pull back can therefore be dangerous. If a person waits to see that sign, the warning may come too late or never appear at all. On March 11th, people along different sections of the Japanese coast experienced the tsunami differently. Some saw the water withdraw, others saw a rapid rise. In muddy harbors, the first obvious sign could be boats moving strangely or water climbing over a quay. The safe rule is simpler than the science. After strong or long coastal shaking, leave the low ground. Fact number 29. Many people lost precious time by trying to do one more thing before leaving. Disaster reports from around the world show the same pattern again and again. People rarely switch instantly from normal life to emergency behavior. They look for family members. They close a shop. They collect documents. They drive home. They check on an elderly neighbor. They wait for a spouse. They move a car. They watch television for confirmation. Many of those actions are understandable. Some are generous. In a tsunami zone, however, each minute can matter. March 11th exposed a painful conflict between helping others and moving quickly enough to survive. A person who goes toward the coast to find someone may place both people at greater risk. A driver who uses a narrow evacuation road can become trapped in traffic with everyone else. Japan's later disaster education put even more emphasis on what is sometimes translated as leading evacuation by example. Move first, and your movement can cause others to follow. The idea is not selfishness. It is that immediate evacuation can save an entire group when hesitation spreads just as quickly as action. Schools became some of the clearest examples of how training could change the outcome. Fact number 30. Disaster education saved children because some schools treated evacuation as a habit, not a theory. In several coastal communities, students had practiced what to do after a strong earthquake. They knew where higher ground was. Teachers knew which routes to use. Some groups kept moving higher when the situation looked worse than expected. The best-known stories came from Kamaishi, where many school children survived after evacuating from tsunami-threatened areas. The phrase Kamaishi miracle became popular afterward, although educators involved have often stressed that survival came from years of preparation and action rather than luck alone. That distinction matters. Calling something a miracle can hide the training behind it. The useful lesson is that drills work best when people understand the reason for the drill. A memorized route may fail if a road is blocked. A person who understands the goal can choose another path and keep going upward. March 11th produced both remarkable survival stories and heartbreaking school tragedies. The difference between them was not always simple, and it would be wrong to turn every outcome into a lesson about individual choices. The tsunami exceeded plans, routes, and designated safe areas in some locations. The successful evacuations became just as important to study as the failures. Fact number 31. Some designated evacuation locations were themselves flooded. Before a disaster, maps create a sense of order. A symbol marks an evacuation building. An arrow points to high ground. A sign tells residents where to gather. March 11th showed the weakness of any plan based on one fixed estimate of danger. In areas where the tsunami exceeded expected heights or reached farther inland than planning maps suggested, places considered safe could become unsafe. That did not mean evacuation maps were useless. It meant they needed to include uncertainty. After the disaster, one of the strongest messages in Japanese tsunami planning became, Do not stop simply because you have reached the first planned destination if the situation tells you to keep moving. If the shaking is extreme, if the sea is rising rapidly, if the warning is upgraded, or if the crowd ahead is moving higher, continue upward when possible. A disaster plan needs a destination, but it also needs permission to abandon the destination. That idea sounds small. It is actually a major change in how emergency systems think. A rigid plan works only for the disaster it predicted. Fact number 32. The tsunami moved up rivers, not only across beaches. A river mouth is an opening in the coastline. During a tsunami, water can travel upstream along the river channel and spread into areas that may not feel like they are directly on the ocean. This happened during the Great East Japan earthquake. Tsunami water entered rivers and estuaries, damaging levees and expanding flood zones. Modern tsunami warnings therefore tell people near rivers, not only people on the immediate coast, to move to safety. It also changes the map of risk. A neighborhood several kilometers inland may still be low and connected to the sea through a river. Bridges become critical points. Roads that look like escape routes can cross channels carrying fast-moving water. River levees can be overtopped or damaged. The water itself also becomes full of objects. A tsunami does not move through a city like clear water in a swimming pool. It picks up wood, cars, boats, containers, signs, furniture, pieces of houses, and fuel tanks. Fact number 33. Cars, boats, and buildings became moving debris. The destructive power of a tsunami comes from more than water depth. A deep, fast flow can move objects that normally seem impossibly heavy. Cars float and collide. Fishing boats are lifted onto roads. Shipping containers become battering rams. Wooden houses can break apart and join the flow. Once that happens, a building standing in the path of the tsunami is not resisting only water. It may be struck repeatedly by large debris. That helps explain why reinforced concrete evacuation structures perform differently from many lighter wooden buildings. Height and structural strength mattered. It is also why returning too early remained dangerous. Even after the fastest surge slowed, floating fuel, broken glass, exposed metal, unstable buildings, and contaminated mud filled the landscape. Rescue teams could not simply drive into many neighborhoods. Roads had vanished under debris or were physically broken. The disaster, therefore, created a logistical problem almost immediately. How do you reach tens of thousands of people when the roads leading to them no longer function? Fact number 34. Road crews opened routes toward the coast like the teeth of a comb. The main north-south expressway and inland roads in Tohoku became lifelines after the earthquake. The Ministry of Land, Infrastructure, Transport, and Tourism organized an emergency clearance strategy often described as the teeth of a comb. The idea was to secure a main inland spine and then clear east-west roads one after another toward devastated coastal communities. Crews pushed aside wreckage, repaired damaged sections, checked bridges, and opened narrow lanes for ambulances, fire engines, military vehicles, fuel trucks, and relief supplies. Speed mattered more than perfection. A road did not need to look normal, it needed to be passable. In some areas, workers restored just enough width for one vehicle to get through. That small opening could reconnect an isolated village with rescue teams. This part of the disaster received much less attention than the tsunami footage, but it shaped what happened afterward. Food, water, blankets, medicine, and fuel are useless if they cannot reach people. Within days, major emergency routes were operating again, even while enormous debris fields remained on both sides. Fact number 35. Japan had to clear cars, containers, nets, and wreckage from harbors before relief ships could enter. The tsunami turned ports into debris fields. Containers had been swept away. Cars and fishing gear sank in channels. Timber and damaged boats blocked access. Even if a relief ship was ready to bring supplies, it could not safely enter a harbor filled with hidden obstacles. After tsunami warnings were lifted, crews began clearing channels. The Ministry of Land, Infrastructure, Transport, and Tourism says work started on March 14th, 3 days after the earthquake. Priority went to important ports such as Miyako, Kamaishi, and Sendai Shiogama. By March 16th, a ship carrying emergency supplies was able to enter Kamaishi. By March 23rd, temporary safe channels had been secured at 10 affected ports. That reopened another route into the disaster zone. The timing was critical because fuel was becoming a serious problem. Vehicles, generators, heating systems, rescue equipment, and hospitals all needed energy at the same time that refineries, roads, ports, and local fuel stations had been disrupted. Fact number 36. Fuel shortages became one of the hidden emergencies after the tsunami. A modern disaster response runs on fuel. Ambulances needed. Fire engines needed. Military trucks needed. Construction equipment needs it. Portable generators needed. People in cold evacuation centers need heating fuel. The earthquake and tsunami damaged supply networks across northeastern Japan. Roads were blocked, ports were unusable, and normal distribution systems had broken down. On March 21st, 10 days after the earthquake, the first oil tanker entered the port of Sendai Shiogama after emergency channel clearing. Over the final part of March, tankers brought tens of thousands of kiloliters of fuel through the port. That detail rarely appears in dramatic documentaries because a fuel tanker arriving safely does not look like a disaster. But recovery depends on thousands of ordinary systems beginning to work again. Water pumps, telephone networks, supermarkets, warehouses, railways, and hospitals all need logistics behind them. Fact number 37. More than 470,000 people were evacuated from their homes. In the immediate aftermath of the Great East Japan earthquake, the number of evacuees rose to more than 470,000. Some had lost homes to the earthquake or tsunami. Others lived in areas threatened by further waves. Many residents of Fukushima were later ordered to leave because of the nuclear emergency. Evacuation centers filled school gyms, community buildings, and other public spaces. Privacy was limited. Heat, medicine, food, water, and sanitation became daily concerns. The Northeast was still cold in March. Snow fell in parts of the disaster region in the days after the tsunami. For elderly people, children, and anyone with a medical condition, evacuation itself carried risk. The same point matters in the Fukushima story. Radiation was not the only health concern. Moving large numbers of vulnerable people quickly, sometimes more than once, created stress and interrupted medical care. The disaster did not end when a person escaped the wave. For many families, that was the beginning of months or years without a permanent home. Fact number 38. More than 120,000 buildings were completely destroyed. The Japanese Reconstruction Agency records roughly 122,000 buildings as completely destroyed, around 283,000 as half destroyed, and more than 748,000 as partially damaged. Those categories include damage from the earthquake, tsunami, fires, ground failure, and related effects across the disaster region. A building count can become abstract, so think about what one destroyed house actually contains: bedrooms, photographs, documents, clothing, appliances, tools, family records, and often a lifetime of possessions. Now multiply that by more than 100,000, then add businesses, fishing facilities, roads, railways, schools, hospitals, local government offices, and utilities. Reconstruction, therefore, was never going to mean simply replacing what had been there before. In many low-lying areas, rebuilding on exactly the same land at exactly the same elevation would reproduce the risk. Some communities chose to move housing to higher ground. Others raised land levels or redesigned coastal districts so that homes, shops, roads, parks, and seawalls formed multiple layers of protection. Those decisions would take years. Fact number 39. The latest Japanese government totals still place the human loss at roughly 20,000 dead, with thousands more never found. The numbers changed for years as records were updated, people who had been missing were identified, and disaster-related deaths were added to official totals. The Japan Meteorological Agency's current table using government damage data updated through March 1, 2026, lists 19,787 deaths, 2,549 people missing, and 6,254 injured. Those figures are more than statistics. They represent families that spent years without answers, communities that lost large shares of their residents, and towns where almost everyone knew somebody who had disappeared. The cause of death also tells us what kind of disaster this really was. Japanese government reporting found that more than 90% of the deaths examined in the hardest-hit prefectures were from drowning. That is very different from the Kobe earthquake, where collapsing buildings caused most of the deaths. Japan's modern earthquake-resistant construction prevented an even larger catastrophe from the shaking itself. The tsunami defeated a different set of defenses. A building can be designed to flex during violent ground motion. It is much harder to protect every home, road, school, hospital, harbor, and low coastal plain from a wall of moving seawater that rises beyond the height people planned for. The casualty map followed the Pacific coast, especially through Iwate, Miyagi, and Fukushima. The financial damage would also reach a scale no previous natural disaster had produced. Fact number 40. It became the costliest natural disaster in modern economic estimates. Japan's Cabinet Office estimated direct physical damage at around 16.9 trillion yen in the months after the disaster. The World Bank later placed the broader economic cost as high as roughly 235 billion United States dollars. That made the Great East Japan earthquake the costliest natural disaster in modern records by widely cited economic estimates. The money was not concentrated in one category. Homes were destroyed, factories stopped, ports and fishing fleets were damaged, roads and railways needed repair, farmland was flooded with salt water, power generation was disrupted, supply chains broke. Japanese factories produced parts used by companies around the world, so shortages reached industries far from the disaster zone. A damaged supplier in Tohoku could slow production at a factory in another country. Then came the cost of the nuclear accident: evacuation, decontamination, compensation, monitoring, storage, and a decommissioning project expected to continue for decades. By the evening of March 11th, that nuclear emergency had already begun, although the most famous images from Fukushima had not happened yet. To understand how the plant went from a successful automatic shutdown to core damage, we need to follow the power. Fact number 41. Fukushima Daiichi had 6 reactor units, but only 3 were operating when the earthquake struck. Fukushima Daiichi Nuclear Power Station sat on the Pacific coast in Fukushima Prefecture. The site had 6 boiling water reactors. On the afternoon of March 11th, Units 1, 2, and 3 were operating. Units 4, 5, and 6 were shut down for maintenance or inspection. When the earthquake hit, the 3 operating reactors automatically shut down, as designed. Control rods entered the reactor cores and stopped the nuclear chain reaction. That sounds like the end of the nuclear danger, but it was only the first step. A reactor that has been shut down still produces heat from the radioactive decay of fission products inside the fuel. The heat falls over time, but it does not disappear the instant the chain reaction stops. That means cooling must continue after shutdown. At first, the plant had a way to do that. The earthquake knocked out the normal external electrical supply, but emergency diesel generators started. For a short period, the safety system was working through exactly the kind of sequence engineers had expected: earthquake, automatic shutdown, loss of outside power, emergency generation. Then the ocean arrived. Fact number 42. The earthquake cut off the plant's normal electrical connection to the grid. Nuclear power stations rely on electricity even when they are no longer producing electricity for customers. Pumps, valves, instruments, lights, control systems, and cooling equipment all need power. When the earthquake damaged the transmission network, Fukushima Daiichi lost its normal off-site power supply. That was serious, but nuclear plants are designed for such a possibility. Emergency diesel generators started automatically. For about 40 minutes, according to the United States Nuclear Regulatory Commission, Those generators provided the electricity needed to keep important systems operating. The detail matters because the earthquake alone did not immediately cause the meltdowns. The reactors shut down. Emergency power started, cooling continued. The accident became far worse when the tsunami flooded the site and disabled much of that backup power as well. In other words, the plant survived the first failure and then lost the system meant to protect it from that failure. Engineers called this kind of problem a loss of multiple layers of defense. Fact number 43. The tsunami at Fukushima Daiichi reached roughly 14 to 15 meters in parts of the site. After the accident, Tokyo Electric Power Company surveyed marks left by the tsunami around Fukushima Daiichi. The company reported inundation heights around 14 to 15 meters on the ocean side of the main building area, with flood depths of roughly 4 to 5 meters over much of the site. That was enough to flood areas containing electrical equipment, emergency generators, and seawater pumps. The difference between height above sea level and flood depth can be confusing, so the important picture is this. Several meters of seawater moved through parts of a nuclear power station that depended on electrical equipment staying dry. At nearby Fukushima Daiichi, another nuclear plant operated by the same company, the flooding pattern was less severe over the main building area. That difference would matter later. At Daiichi, the water knocked out much of the emergency power that had taken over after the earthquake. Fact number 44. Several reactor units entered a station blackout. A station blackout means that a nuclear plant loses the alternating current electrical power normally available from both the grid and on-site emergency sources. At Fukushima Daiichi, the tsunami flooded electrical rooms and disabled emergency generators at several units. Batteries could provide some direct current power for instruments and controls, but batteries do not replace a full electrical system forever. Operators were suddenly working inside a damaged plant with poor lighting, unreliable instruments, communication problems, aftershocks, flooding, and a rapidly changing reactor condition. Some readings were unavailable. Others had to be checked locally. Crews carried equipment through dark buildings. Portable generators and cables were brought in, but connecting outside equipment to a flooded, damaged nuclear site is not as simple as plugging an extension cord into a wall. Every hour mattered because the fuel inside the shut reactors was still hot. If enough water boiled away, the fuel rods could become uncovered. Fact number 45. A shutdown nuclear reactor can still overheat badly if cooling is lost. This part of the Fukushima accident is easy to misunderstand. When the control rods entered the cores on March 11th, the nuclear fission chain reaction stopped. The reactors were no longer running normally. But radioactive materials created during operation continued to decay. That decay released heat. Immediately after shutdown, decay heat can still be a significant fraction of the reactor's previous thermal power. It gradually falls, but the fuel needs continuous cooling while that happens. At Fukushima Daiichi, the loss of power made it increasingly difficult to keep enough water over the fuel in units 1, 2, and 3. As water levels fell, portions of the fuel became exposed. Temperatures rose. Fuel cladding was damaged. Reactor cores began to melt. So the phrase automatic shutdown can be misleading to people outside the nuclear industry. Shutting down the chain reaction is essential, but it does not turn a reactor into a cold piece of machinery. The next task is removing heat. Fukushima Daiichi lost that ability at exactly the moment when the surrounding region was dealing with one of the largest natural disasters in Japanese history. Fact number 46. Unit 1 developed the first major crisis. Unit 1 was the oldest operating reactor at Fukushima Daiichi. After the tsunami, its cooling situation deteriorated quickly. Water levels dropped and the core was damaged. Inside the reactor, extremely hot zirconium alloy around the fuel reacted with steam. That chemical reaction produced hydrogen gas. Hydrogen is dangerous because it can burn or explode when mixed with air in the right proportions. pressure was also rising inside the containment system. Operators needed to reduce pressure while trying to add water and protect the containment structure. This placed them in an awful engineering situation. Venting pressure could help protect the reactor containment, but gases released through the process could contain radioactive material. Delaying venting could allow pressure to climb. On top of that, valves and instruments depended on power, compressed air, and access to areas that had been damaged. By the morning of March 12th, people outside the plant were already being moved farther away. That afternoon, the first explosion made the crisis visible to the entire world. Fact number 47. The Unit 1 reactor building exploded on the afternoon of March 12th. At about 3:36 in the afternoon on March 12th, a hydrogen explosion tore through the upper part of the Unit 1 reactor building. Television cameras captured the blast. A sudden cloud expanded above the building, and the outer structure around the top floors was badly damaged. For viewers around the world, this was the moment Fukushima changed from a complicated emergency into a terrifying image. The explosion did not mean the reactor had detonated like a nuclear bomb. A commercial nuclear reactor cannot explode in the same way as a nuclear weapon. The blast was caused by hydrogen that had accumulated in the building. That distinction matters, but it did not make the situation harmless. The explosion damaged the building, injured workers, complicated emergency work, and increased concern about radioactive releases. It also demonstrated that hydrogen generated by overheating fuel had escaped from the reactor system into areas where it could mix with air. After the explosion, crews still had to do the same urgent thing they had been trying to do before it: get water into the reactor. Fact number 48. Seawater injection was a desperate step because it effectively sacrificed the reactor to save the situation. A nuclear power reactor is not designed to be filled with ocean water during normal operation. Salt water is corrosive. Injecting it into a damaged reactor makes future recovery of the unit far more difficult and can permanently ruin equipment. But by March 12th, preserving Unit 1 as a power-producing asset was no longer the priority. Cooling the damaged fuel was. Emergency crews used available systems, including firefighting equipment, to inject water. Seawater was introduced because fresh water supplies and normal injection systems were limited or unavailable. The nature of the emergency becomes clear here, even without technical language. Operators were no longer trying to save a valuable machine. They were trying to stop the machine from becoming more dangerous. The same basic problem was developing in the other operating reactors. Fact number 49. Unit 3 suffered its own hydrogen explosion 2 days after Unit 1. Unit 3 had also shut down automatically after the earthquake. It also lost much of its cooling capability after the tsunami. As the core overheated and water levels fell, fuel damage produced hydrogen. At about 11:01 in the morning on March 14th, an explosion struck the Unit 3 reactor building. The blast appeared more violent in television footage than the earlier Unit 1 explosion. A dark column of debris and smoke rose above the building. Workers were injured, and emergency operations were disrupted again. The repeated explosions created an especially frightening public impression. The accident did not look as though it was stabilizing. It looked as though a new reactor building might explode every day. That fear was not irrational. Operators were managing several damaged units at once, each with different conditions and limited instrumentation. Then, early on March 15th, another serious event occurred near Unit 2, while Unit 4 was also found badly damaged. For the public, the plant now looked like a row of broken buildings. Fact number 50. Unit 2 may have been a major source of radioactive release, even though its building did not show the same dramatic explosion. Unit 2 did not produce the same famous exterior blast image as Units 1 and 3. But early on March 15th, workers heard an abnormal noise near the pressure suppression chamber, and pressure in that part of the containment system dropped. The exact sequence inside Unit 2 was difficult to reconstruct in real time because instruments were damaged and conditions were severe. Later analysis concluded that Unit 2 also suffered major core damage. The outside image could therefore be misleading. The most dramatic picture is not always the most important part of a technical accident. A building can look less damaged from outside, while serious failures are occurring inside systems that cameras cannot see. Radioactive material was released from the site through several pathways during the accident, including venting and leaks from damaged systems and buildings. Weather then affected where that material traveled. Some areas northwest of the plant received more contamination than simple circular distance from the station would suggest. That would later complicate evacuation zones and decontamination. Fact number 51. Unit 4 exploded even though its reactor was not operating when the earthquake happened. This became one of the strangest parts of the Fukushima story. Unit 4 had been shut down for a scheduled inspection before March 11th. The reactor itself was not producing power when the earthquake struck. Yet, on the morning of March 15th, an explosion damaged the upper part of the Unit 4 reactor building. How could a shut-down reactor building suffer a hydrogen explosion? Later investigation found that hydrogen produced in Unit 3 could travel through shared exhaust connections and enter Unit 4. The gas then accumulated in the Unit 4 building and exploded. The International Atomic Energy Agency later highlighted this as a safety lesson. Connections between reactor units can allow an accident in one unit to affect another. The Unit 4 explosion also intensified fears about its spent fuel pool, where used nuclear fuel was stored underwater. For a period, outside observers worried that pool water levels might be dangerously low. Fact number 52. Spent fuel pools became a major concern because used fuel also needs cooling. Nuclear fuel does not stop producing decay heat when it is removed from a reactor. Used fuel is normally stored in deep pools of water. The water removes heat and provides shielding from radiation. During the Fukushima emergency, loss of power and damage to reactor buildings raised concern about the condition of several spent fuel pools, especially at Unit 4. Information was limited. Damage made access difficult. Steam seen around buildings added to uncertainty. Japanese forces used helicopters to drop water in the area, while fire trucks and later large concrete pump vehicles were used to deliver water toward spent fuel pools. Some of the most dramatic scenes showed military helicopters hovering above the damaged plant with loads of water. The operation demonstrated how far the response had moved from normal nuclear procedure. A machine normally used to place concrete at construction sites became useful because its long articulated boom could position a water line near a heavily damaged building. Fact number 53. Fire engines became part of the reactor cooling system. Firefighting equipment is designed to move large amounts of water under difficult conditions. At Fukushima Daiichi, that ability became essential after normal reactor injection systems lost power or became unusable. Crews connected fire engines and temporary lines to inject water into damaged reactors and spray or refill spent fuel pools. A fire truck becoming part of a nuclear cooling system shows how completely the emergency had crossed normal boundaries. But every improvised solution created new difficulties. Seawater carried salt. Hoses leaked. Connections had to be made in areas with radiation and debris. Pumps needed fuel. Workers needed dosimeters and protective equipment. Aftershocks could interrupt operations. The plant was not operating as a designed industrial system anymore. It was being held together by a growing collection of temporary systems. Emergency crews mattered because every temporary cooling route bought time. Fact number 54. The phrase Fukushima 50 became famous, but the emergency workforce was much larger than 50 people. During the worst days of the accident, international media began using the phrase Fukushima 50 for the workers who remained at the station. The label created a powerful image of a tiny group standing between Japan and a larger nuclear disaster. The reality was more complicated. Staffing levels changed. Different teams rotated in and out. Tokyo Electric Power Company employees, contractors, firefighters, self-defense force personnel, police, and other specialists all participated in emergency work. At certain moments, non-essential personnel were moved away from the most dangerous areas, leaving smaller groups to perform urgent tasks. But the full response involved far more than 50 individuals. The simplified nickname survives because it captures something real. Workers entered damaged areas with limited information, high heat, darkness, aftershocks, and radiation hazards to restore cooling and power. Some suffered injuries and significant radiation exposure. The World Health Organization later found no acute radiation deaths among workers or the public from the accident. But that does not mean the working conditions were safe or easy. Fact number 55. The evacuation zone expanded rapidly as the nuclear situation worsened. On March 11th, as cooling problems developed, the Japanese government ordered residents within roughly 3 kilometers of Fukushima Daiichi to evacuate and told people within about 10 kilometers to shelter indoors. The next day, the evacuation order expanded to 20 kilometers. By March 15th, people in the zone from 20 to 30 kilometers were instructed to shelter indoors. Later, the map became more complex because radioactive contamination did not spread in a perfect circle. Wind and rain carried material in particular directions, and some communities farther away received higher deposition than areas at similar distances in other directions. In April, Japan created additional planned evacuation areas based on projected radiation exposure. This rapid expansion created confusion and repeated movement for some residents. Families left one shelter and moved again. Hospitals and care facilities had to transport vulnerable patients. For many people, leaving home was supposed to be temporary. Fact number 56. More than 100,000 people were evacuated because of the nuclear accident. The Reconstruction Agency reports that evacuation zones connected to Fukushima Daiichi caused roughly 110,000 people to leave their homes, while the broader number of evacuees from Fukushima Prefecture eventually rose much higher when people displaced by the earthquake and tsunami are also included. At this point, the disaster became different from a normal tsunami recovery. In a town destroyed by water, the reason a resident cannot return is visible. The house may be gone. The road may be broken. In a nuclear evacuation zone, a house can still be standing. A family car can still be in the driveway. Clothes can still be in closets. Yet, residents may be told not to live there because of contamination that cannot be seen or smelled. That invisible risk created a different kind of uncertainty. People worried about children, food, soil, livestock, and whether their hometown would ever reopen. Some evacuation orders were lifted within a few years. Others remained much longer. A small portion of Fukushima would still have difficult-to-return areas more than a decade later. The word temporary turned into an entire chapter of people's lives. Fact number 57. Fukushima Daiichi, another nuclear power station only a short distance away, also lost important cooling systems but avoided a meltdown. Fukushima Daiichi sits south of Fukushima Daiichi and was hit by the same earthquake and tsunami. Several of its reactors lost the ability to remove heat through normal seawater systems after flooding. The difference was that enough equipment remained recoverable for workers to restore cooling. Crews repaired or replaced seawater pumps, laid long power cables, and brought reactors to cold shutdown. The International Atomic Energy Agency later described the event at Fukushima Daiichi as a serious incident, but not a core-damaging accident like Daiichi. This comparison is extremely useful because the two plants faced the same regional catastrophe, but did not experience the same final outcome. Small differences in site flooding, surviving electrical equipment, access, and the ability to restore heat removal changed the result. Complex disasters often work this way. A few meters of water, the position of one generator, or one usable power line can separate a major accident from a controlled emergency. The accident was not caused by the loss of one single device. It came from several layers of protection being defeated together. Fact number 58. The nuclear accident was eventually rated at the highest level on the International Event Scale. The International Nuclear and Radiological Event Scale runs from lower-level anomalies and incidents up to level 7, described as a major accident. Fukushima Daiichi was initially given lower provisional ratings while the situation was still developing. On April 12, Japanese authorities re-evaluated the accident and rated it level 7 because of the amount of radioactive material released. Chernobyl in 1986 had also been rated level 7. That does not mean Fukushima and Chernobyl were identical accidents. They involved different reactor designs, different accident sequences, different releases, and very different immediate health consequences. The scale is not a ranking where every event at the same level has the same story. Level 7 tells us that Fukushima was a major nuclear accident with significant release of radioactive material beyond the plant. For the public, the comparison with Chernobyl created fear. Fact number 59. Radioactive iodine and cesium became two of the most closely watched contaminants. Different radioactive materials behave differently in the environment and in the human body. After Fukushima, iodine-131 and cesium-137 received particular attention. Radioactive iodine can be taken up by the thyroid gland. It has a relatively short half-life of about 8 days, so its radiation level falls quickly over weeks, but it is especially important during the first phase of an accident. Cesium-137 lasts much longer. Its half-life is about 30 years. It can contaminate soil and require long-term monitoring and cleanup. Japan began large-scale testing of air, soil, water, milk, vegetables, fish, and other food products. Restrictions were placed on some foods from affected areas when measurements exceeded limits. For people living far from the plant, these tests mattered because radiation cannot be judged by appearance. A vegetable looks the same whether its cesium level is high or low. Measurement is the only reliable answer. Fact number 60. There were no acute radiation deaths among the public or workers from the Fukushima accident. The distinction matters because the nuclear accident is often mixed together with the death toll from the earthquake and tsunami. The World Health Organization says there were no acute radiation injuries or deaths among workers or members of the public caused by radiation exposure from the Fukushima Daiichi accident. The approximately 20,000 deaths associated with the Great East Japan disaster were overwhelmingly connected to the earthquake, tsunami, and later disaster-related health effects, not immediate radiation sickness. That does not mean the nuclear accident was harmless. It caused mass evacuation, contamination, enormous economic loss, long-term cleanup, psychological stress, and additional health risks for some more highly exposed workers and residents. But accuracy matters. Saying thousands died from Fukushima radiation would be false. The distinction also helps explain why international health agencies focus on long-term cancer risk rather than an epidemic of acute radiation sickness. The scientific picture that emerged over the following decade was much less dramatic than many early public fears. Fact number 61. International health agencies did not expect a clearly observable increase in cancer rates for the general population. The World Health Organization's major assessment concluded that predicted radiation-related health risks for the general population inside and outside Japan were low. It did identify higher estimated risks for certain cancers in specific groups living in the most affected areas, especially where estimated doses were highest. And it recommended long-term monitoring. The United Nations Scientific Committee on the Effects of Atomic Radiation later reviewed hundreds of studies and concluded that no adverse health effects among Fukushima residents had been documented that could be directly attributed to radiation exposure from the accident, and that future radiation-linked increases in cancer were unlikely to be detectable at the population level. The scientific wording is deliberately careful. It is not a claim that radiation is safe. Radiation risk depends on dose. Workers with higher exposures required follow-up. Certain populations received more attention than others. But the evidence did not support the apocalyptic health predictions that circulated during the first days of the crisis. The strongest evidence, therefore, points to a disaster whose largest health burden came from the tsunami, evacuation, disruption, and long-term displacement, rather than a wave of acute radiation illness. Fact number 62. Evacuation itself created serious health risks. Moving people out of danger is essential, but evacuation is not medically neutral. Elderly residents can lose access to regular doctors. Patients may be moved without complete records. People with dementia can become disoriented. Medicine can run out. Families are separated. Stress rises. Physical activity changes. After Fukushima, researchers and government agencies studied health problems connected to evacuation and long-term displacement, including psychological distress and changes in chronic disease risk. The United Nations Scientific Committee noted increases in some cardiovascular and metabolic conditions among evacuees, probably connected to social and lifestyle changes rather than radiation exposure. This matters because emergency decisions often involve choosing between risks, not choosing between risk and no risk. Leaving a contaminated area reduces radiation exposure. Moving a frail patient can create another danger. Officials had to make those decisions while the reactor condition was changing by the hour. The phrase nuclear disaster can make the story sound like radiation was the only threat. Fact number 63. Radiation contamination did not spread in a perfect circle around the plant. Early evacuation zones were based mainly on distance because distance is simple to communicate during an emergency. But radioactive material moves with air and weather. Wind direction, rain, and snow can carry contamination farther in one direction while leaving another area at a similar distance with much lower levels. After Fukushima, measurements showed a plume of higher contamination extending northwest from the plant. That meant some communities outside the original circular zones required later evacuation or special controls. It also explains why maps of Fukushima contamination look irregular rather than like a target with perfect rings. Here again, measurement replaced assumption. Mobile monitoring vehicles, aircraft, fixed posts, soil samples, and food testing gradually produced a much clearer picture. Over time, radioactive decay, weather, cleanup, and removal of contaminated material reduced dose rates in many areas. Fact number 64. The accident changed the meaning of ordinary things like soil, rainwater, and leaves. After a radiological release, contamination can settle onto roofs, roads, trees, fields, and soil. In Fukushima, cleanup teams washed surfaces, removed vegetation, scraped topsoil in selected areas, and collected contaminated material for storage. This created a new logistical problem. Cleaning one place creates material that must be stored somewhere else. Bags of removed soil and vegetation became a familiar sight in parts of Fukushima during the decontamination years. Japan eventually constructed large interim storage areas near Fukushima Daiichi for removed soil and waste from decontamination. The scale is difficult to picture because the material is not highly radioactive nuclear fuel. It is ordinary dirt, leaves, and debris containing enough radioactive cesium to require controlled handling. Nuclear accidents can therefore remain expensive long after reactors are stable. The problem spreads into land management, farming, waste transport, public trust, and local politics. Fact number 65. Keeping the melted reactor fuel cool created contaminated water for years. After the accident, water had to keep flowing into the damaged reactors to remove heat from melted fuel debris. At the same time, groundwater and rainwater entered damaged reactor and turbine buildings. When that water contacted contaminated areas, it picked up radioactive materials. Tokyo Electric Power Company built systems to pump, treat, store, and reuse large volumes of water. Tanks spread across the site. Engineers also tried to reduce the amount of new groundwater entering the buildings. Measures included pumping groundwater before it reached contaminated zones, paving surfaces, improving drainage, and building an underground frozen soil barrier around parts of the reactor area. The name frozen wall sounds futuristic, but the concept is straightforward. Pipes in the ground circulate coolant and freeze surrounding soil, reducing the movement of groundwater through it. The water problem became one of the defining engineering challenges of the decommissioning project. Fact number 66. Japan began releasing treated water from the site into the Pacific in 2023 under a monitored plan. The water stored at Fukushima was treated through a system designed to remove many radioactive substances. One isotope, tritium, is difficult to separate from water because tritium is a radioactive form of hydrogen and can become part of the water molecule itself. Japan decided to dilute treated water and release it gradually into the Pacific under regulated limits. The plan became controversial in Japan and neighboring countries, especially among fishing communities worried about reputation and consumer trust. The International Atomic Energy Agency reviewed the plan and established its own monitoring activities. The agency said the planned discharges, if carried out as described, would have a negligible radiological impact on people and the environment. The release began in 2023 and continued under monitoring. For the purpose of understanding the 2011 disaster, the important point is how long the chain continued. Fact number 67. The plant was declared to have reached a cold shutdown condition in December 2011, but that did not mean the cleanup was finished. By December 2011, the Japanese government announced that the damaged reactors had reached what it called a cold shutdown condition. Temperatures were being kept low and radioactive releases had been greatly reduced. That marked the end of the emergency stabilization phase. But the phrase cold shutdown can sound more final than it was. These were not intact reactors waiting to restart. Units 1, 2, and 3 contained melted fuel debris. Buildings were damaged. Contaminated water remained. Radiation made access difficult. The next phase was decommissioning, and that task was expected to take decades. Robots and remote equipment would have to inspect areas too radioactive for long human entry. Engineers needed to determine where the melted fuel had gone, how solid it was, what structures remained stable, and how material could eventually be removed. In some ways, the crisis became quieter after December. There were fewer dramatic explosions and fewer breaking news banners. Fact number 68. Melted fuel debris is still one of the hardest parts of the decommissioning job. When reactor fuel overheated at Fukushima Daiichi, portions of the fuel, metal cladding, and structural materials melted and mixed together. This material is called fuel debris. It is highly radioactive and sits inside damaged reactor containment systems that were never designed to be dismantled under these conditions. Engineers cannot simply send workers inside with tools. Radiation levels, narrow access points, water, damaged structures, and uncertain debris shapes make direct work difficult. Much of the investigation has therefore been done remotely. Robots, cameras, sensors, and specially designed devices have entered containment vessels to map conditions. The goal is to retrieve fuel debris gradually, beginning with very small trial quantities and learning from each step. As of 2026, Tokyo Electric Power Company described fuel debris retrieval as the central new phase of decommissioning, and continued internal investigations using specialized equipment, including microdrones in Unit 3. 15 years after the earthquake, the physical remains of the accident were still inside the reactors. Fact number 69. The Fukushima accident changed nuclear safety rules far beyond Japan. Nuclear regulators around the world studied what had happened at Fukushima Daiichi. The central lesson was not simply build a higher seawall. The deeper lesson was to assume that several safety systems might fail together during an extreme natural event. In the United States, the Nuclear Regulatory Commission ordered plants to strengthen strategies for maintaining cooling and other key functions after the loss of normal and emergency power. Plants added portable pumps, generators, connections, and improved spent fuel pool monitoring. The International Atomic Energy Agency reviewed emergency planning, natural hazard assessments, communication, multi-unit accidents, and protection of electrical equipment against flooding. One lesson was especially clear. Historical records alone may not capture the largest possible natural hazard. An event that has not happened during the period of modern observation can still happen. Fukushima changed the way engineers discuss events beyond the original design basis. Fact number 70. The nuclear crisis happened at the same time as one of the largest rescue operations Japan had ever attempted. It is easy to tell the Fukushima story as though the nuclear plant existed by itself. It did not. The same earthquake and tsunami had destroyed coastal towns, cut roads, flooded hospitals, damaged ports, and displaced hundreds of thousands of people. Every helicopter sent toward the nuclear site was a helicopter that had to be coordinated with a much larger national emergency. Fuel, protective suits, pumps, food, generators, and medical teams all competed for damaged transportation networks. The Japanese self-defense forces mobilized on an unprecedented scale. Police, firefighters, Coast Guard crews, local officials, volunteers, foreign military personnel, and aid organizations worked across the region. The United States launched Operation Tomodachi to support Japan with humanitarian assistance, logistics, search operations, airlift, and technical support. The word Tomodachi means friend. That operation would become one of the largest examples of United States and Japanese military cooperation in a disaster. It is hard to imagine a clearer example of damaged infrastructure becoming useful again under pressure. Fact number 71. Sendai Airport came back to life far faster than its first images suggested it could. When the tsunami crossed Sendai Airport, the scene looked almost terminal. Water covered the runways. Cars, wood, mud, and wreckage were scattered across the airfield. Aircraft had been damaged. Parts of the terminal were surrounded by water. For anyone watching the footage that afternoon, it was easy to imagine the airport being unusable for months. But an airport is more than a place where passengers catch flights. In a disaster, it can become a lifeline. Heavy equipment, rescue teams, medicine, food, fuel, and personnel can move through an airport much faster than through roads that have been blocked or washed away. That made clearing Sendai Airport urgent. Crews pumped away enormous amounts of water, removed debris, inspected pavement, restored basic systems, and opened space for emergency aircraft. Military and civilian teams worked around damaged infrastructure instead of waiting for the entire airport to look normal again. Less than 5 weeks after the tsunami, limited commercial passenger service returned on April 13th. Think about that turnaround. On March 11th, waves were pushing cars across the airport grounds. By the middle of April, passengers were flying through it again. The terminal still needed repairs, and full recovery took longer, but the early reopening became a useful symbol of how reconstruction actually worked. Nobody waited for perfect conditions. A road only had to become passable before relief trucks could use it. A port only had to have a safe channel before vital cargo could enter. An airport only had to recover enough functions to become useful again. And Sendai Airport became useful very quickly. Fact number 72. Operation Tomodachi eventually involved tens of thousands of United States military personnel. The name sounded unusually gentle for a military operation. Tomodachi means friend in Japanese. The operation began almost immediately after the disaster, as the United States military moved ships, aircraft, helicopters, supplies, and personnel toward Japan. According to the United States Department of Defense, roughly 24,000 American service members, 189 aircraft, and 24 naval ships participated over the course of the response. Their work was not limited to one dramatic rescue mission. Aircraft transported food, water, blankets, and equipment. Helicopters reached communities that were difficult to access by road. Ships provided logistics and aviation support offshore. American forces helped reopen Sendai Airport, moved supplies, and worked with Japanese authorities while the Fukushima emergency added an entirely different layer of risk. For many service members, the mission meant operating in a landscape where the basic map was no longer reliable. Roads shown on maps might end in debris. Coastal landmarks had disappeared. Airfields and ports had been flooded. Communications were damaged. Aftershocks continued. And, unlike a conventional military operation, the enemy was not another force. It was distance, destroyed infrastructure, cold weather, missing information, and time. Operation Tomodachi lasted into early May, but its effect went beyond the supplies that were delivered. The disaster forced the two countries to coordinate at a scale that would have been difficult to rehearse in advance. Japan was already carrying out a domestic response of extraordinary size. The American operation was supporting that effort, not replacing it. Fact number 73. Japan's self-defense forces carried out their largest disaster relief operation up to that point. Within hours of the earthquake, Japan began expanding the number of self-defense force personnel assigned to the disaster zone. The mission grew rapidly because the emergency was not concentrated in one city. The affected region stretched across a vast section of the Pacific coast. Some communities needed search teams, others needed water, hospitals needed fuel and medical transport, shelters needed food and blankets, roads had to be opened, bodies had to be recovered. Helicopters had to reach isolated areas. At the same time, personnel were being sent to support the response around Fukushima Daiichi. At the peak, roughly 100,000 self-defense force personnel were mobilized for the disaster response. That number matters because Japan's self-defense forces had to do several different jobs at once. They were search and rescue teams, transport crews, engineers, logistics workers, medical support, and sometimes the only organized connection between an isolated town and the outside world. The scale also exposed a basic truth about giant disasters. The first challenge is not always a lack of supplies. Sometimes the supplies exist, but there is no simple way to move them where they are needed. A warehouse full of bottled water is not useful to a mountain shelter if the road between them is buried. Fuel at a refinery does not help an ambulance if the distribution system is broken. A rescue team cannot search a neighborhood until someone has found a route into it. The response became, to a surprising degree, a problem of movement. Fact number 74. Japan received offers and assistance from well over 100 countries and regions. The disaster triggered an international response that reached far beyond Japan's closest allies. Japan's Ministry of Defense later said the country had received support from 159 countries and regions, and 43 international organizations, along with private groups and individuals around the world. Some assistance came in the form of specialized rescue teams. Some countries sent medical support, search dogs, blankets, food, water, equipment, or financial aid. Others provided technical expertise for the nuclear emergency. The diversity of that response is worth noticing. A tsunami on the northeastern coast of Japan quickly became a global humanitarian event. Rescue personnel arrived, speaking different languages and carrying different equipment, but they were entering the same damaged towns and working around the same broken roads. International support also arrived from countries that had experienced their own major earthquakes and tsunamis. In disaster work, experience travels. A rescue team that has searched collapsed buildings after one earthquake may bring knowledge that becomes useful thousands of miles away years later. The response did not erase the practical difficulties. Foreign teams still needed transportation, interpreters, maps, assignments, accommodation, and coordination. More people can help only if someone can put those people where they are useful. Disaster management often looks less dramatic than the images shown on television. Coordination rarely looks heroic. It looks like lists, radio calls, fuel schedules, route maps, warehouses, and exhausted people making decisions in rooms filled with information. Fact number 75. Temporary housing became an emergency project on a national scale. Surviving the tsunami did not mean the crisis was over. Hundreds of thousands of people had lost homes, been evacuated, or could not safely return. Many initially stayed in schools, gymnasiums, community centers, public buildings, and other emergency shelters. March in northeastern Japan can be cold. Some shelters had limited heating. Electricity and water were unreliable in badly affected areas. Families slept close together with very little privacy. Elderly people, young children, and anyone who needed regular medical care faced additional risks. Japan therefore had to move from emergency shelter to temporary housing as quickly as possible. Prefabricated housing communities began appearing on available land. They were not intended to be permanent towns. They were a bridge between the night of the disaster and whatever came next. That bridge lasted much longer for some families than anyone wanted. Rebuilding a house is one thing. Rebuilding a neighborhood whose original land may still be inside a tsunami hazard zone is much more complicated. Before permanent homes could be built, communities had to decide whether they would return, move uphill, raise the land, redesign roads, or abandon certain low areas altogether. Those decisions involved property rights, family ties, jobs, schools, fishing ports, elderly residents, budgets, and engineering. A person could receive a temporary home in weeks and still wait years for a permanent answer. The reconstruction was therefore not simply about replacing what the water had destroyed. In many places, Japan decided that putting everything back exactly where it had been would recreate the same vulnerability. That decision led to one of the largest community relocation programs in the country's modern history. Fact number 76. Entire neighborhoods were moved to higher ground. After the tsunami, some towns faced a brutal planning question. If a neighborhood had just been destroyed by the sea, should homes be rebuilt on the same land? For many communities, the answer was no. Japan's Reconstruction Agency reported collective relocation projects involving 224 districts in 26 municipalities. The goal was straightforward to describe and enormously difficult to execute. Move residential areas away from the most dangerous low ground and build new communities at higher elevations. That meant more than constructing houses on hills. New roads had to reach the new sites. Water, sewage, electricity, schools, shops, and public services had to follow. Hillsides sometimes had to be cut and prepared. Residents had to agree on relocation plans. Land had to be purchased or reorganized. And while engineers worked, families remained in temporary housing. There was another problem. A fishing town cannot simply move everything away from the sea. Fishing boats still need ports. Seafood businesses still need coastal access. Tourism may depend on beaches and waterfronts. Industry may depend on flat land near transportation routes. So many towns began separating functions. Homes could move uphill, while ports, warehouses, parks, or commercial facilities remained closer to the coast. This was not retreat in the simple sense. It was an attempt to decide which parts of daily life absolutely needed the shoreline and which did not. By the end of 2020, the development of residential sites for relocation to higher ground was essentially complete. Fact number 77. The rebuilt coast did not rely on one giant wall to solve the tsunami problem. After March 11th, new seawalls became a highly visible symbol of reconstruction. In some places, coastal defenses were rebuilt higher or stronger. But the deeper lesson of the disaster was that a single structure should not be treated as an absolute guarantee. The tsunami had already demonstrated why. A wall can reduce the force of a smaller wave. It can delay flooding. It can protect against more frequent events. But an extreme tsunami may overtop it, damage it, or simply arrive higher than the event used in the original design. So Japan increasingly emphasized layered protection. A coastal wall might be one layer. Raised roads could become another. Parks and open spaces could occupy areas expected to flood. Homes could be moved higher. Evacuation towers and tall buildings could provide vertical escape where hills were too far away. Warning systems could provide information. Schools could practice evacuation routes. None of those measures is perfect by itself. Together, they make it harder for one wrong assumption to become fatal. That idea is important because the old instinct in engineering is often to ask, what is the maximum event this structure must survive? March 11th forced a different question. What happens when nature produces something larger than the number we designed for? That question did not apply only to seawalls. It applied to nuclear plants, backup generators, communication systems, evacuation maps, and warning messages. Fact number 78. Japan changed the way it warns people about giant tsunamis because of what went wrong in 2011. The Japan Meteorological Agency issued a tsunami warning very quickly on March 11th. The problem was not the speed of the first warning. The problem was the scale attached to it. The earthquake was so large that the first rapid estimate underestimated its true magnitude. That led to initial tsunami height estimates that were also too low in some areas. For an ordinary earthquake, rapid calculations work well enough to issue useful numbers. For an extraordinary magnitude 8 or magnitude 9 event, the first minutes are much harder. The seismic instruments can effectively run into the limits of the quick method before scientists have enough information to understand the full rupture. Japan redesigned the system. The improved tsunami warning method went into operation in March of 2013. If an earthquake appears so enormous that its exact magnitude cannot be reliably calculated immediately, the agency no longer has to pretend that an early, precise number is trustworthy. It can use the maximum expected magnitude for that region and issue stronger warnings based on the possibility of a giant event. The language changed too. Instead of giving people a falsely reassuring small number during the uncertain opening minutes, warnings can use simple qualitative words indicating an extremely large tsunami. That may sound like a minor change in wording. It is not. In a coastal disaster, the first message can shape the next 10 minutes of a person's behavior. For a coastal family deciding whether to leave immediately, those minutes are the whole point of the system. Fact number 79. The new warning system deliberately uses words such as huge when the first numbers cannot be trusted. One lesson sounds counterintuitive. Sometimes a less precise warning can be more honest and more useful. People tend to trust numbers. If a warning says 3 meters, the mind creates an image of 3 meters. Someone standing on a seawall higher than that may feel protected. Someone living farther inland may decide there is time to collect belongings. But during a magnitude 9 earthquake, the early 3-meter estimate may not mean the tsunami will actually stop at 3 meters. It may mean the measuring system has not yet captured the true size of the earthquake. Japan's revised warning method addresses that problem directly. For an exceptionally large earthquake whose size cannot be determined quickly, the first warning can avoid giving an underestimated numerical wave height. Instead, the message uses language such as huge for the highest category. The purpose is not drama. The purpose is behavior. A person who hears huge should not be calculating whether a particular wall is high enough. The message is designed to push that person toward immediate evacuation. Later, as better measurements arrive from offshore instruments and coastal gauges, the warning can become more specific. Here, uncertainty itself became part of the safety message. The system essentially says, we do not yet know exactly how large this is, and that uncertainty is a reason to move, not a reason to wait. That lesson came from the first minutes of the main shock. Fact number 80. The aftershock sequence was enormous. A magnitude 9 earthquake does not release energy and then leave the crust instantly peaceful. The surrounding fault system has been violently rearranged. Stress has changed across a huge region. For days, weeks, months, and years afterward, the crust continues to adjust. The Tohoku earthquake produced an extraordinary number of aftershocks. By May of 2012, the Japan Meteorological Agency had counted more than 100 earthquakes of magnitude 6 or greater in the broader aftershock activity, and more than 670 of magnitude 5 or greater. For people in the affected region, those numbers were not abstract. Imagine sleeping in a shelter after losing your home and feeling the floor move again. Imagine working inside a damaged building when another strong shock begins. Imagine crews repairing a port while tsunami advisories and aftershock warnings remain part of daily decision-making. Every aftershock raised the same question for a few seconds. Is this another major event? Some were powerful enough to interrupt recovery operations. Others caused additional damage or temporary tsunami warnings. Even smaller shocks could be psychologically exhausting because they returned people to the sensation of the original disaster. Aftershocks also complicated engineering inspections. A building judged usable after the main shock might need to be checked again after another strong event. The sequence slowly became less active but it did not disappear quickly. And one of the strongest aftershocks came so soon after the main earthquake that the first tsunami was still racing toward parts of the coast. Fact number 81. The largest early aftershock struck less than half an hour after the main earthquake. At about 3:15 in the afternoon on March 11th, roughly 29 minutes after the magnitude 9 main shock began, another major earthquake struck off Ibaraki Prefecture. The Japan Meteorological Agency later identified it as the largest aftershock in the early sequence, with a magnitude around 7.6 by its analysis. That would be a major earthquake in almost any other context. On this day, it arrived while the country was still trying to understand the first one. The timing is difficult to appreciate from a neat disaster timeline. Newsrooms were receiving reports of shaking. Emergency managers were tracking tsunami warnings. Coastal residents were evacuating. Trains were stopped. Power was failing. The first destructive waves were reaching parts of Tohoku. Then another earthquake, large enough to cause severe shaking, hit the system. Within the first 40 minutes, several magnitude 7 class earthquakes occurred across the enormous rupture region. This mattered for both people and instruments. A tide gauge already damaged by the tsunami could stop sending information. A weather station could lose power. A communication line could fail just when it was most valuable. The disaster therefore attacked the observation network at the same time the network was needed to measure the disaster. That sounds almost unfair, but it is a recurring problem in extreme events. Sensors are placed near the hazards they are supposed to observe, which means the biggest event may destroy the sensors. Fact number 82. The tsunami and earthquake knocked many weather and ocean observation stations offline. Modern disaster response depends on data that most people never see. Seismometers report ground motion. Tide gauges report sea level. Weather stations report wind, temperature, and precipitation. Communication networks move those measurements to agencies that turn them into warnings and forecasts. On March 11th, parts of that network were damaged by the same forces they were measuring. The Japan Meteorological Agency reported problems at numerous seismometers, seismic intensity stations, automated weather stations, and tide gauges in northern Japan. Some were physically damaged, others lost power or communication links. This created blind spots precisely when officials wanted more information, not less. Recovery teams had to restore observation sites while the emergency continued. By the following spring, most of the damaged systems had been brought back. There is a useful lesson hidden inside that technical detail. A warning system is not one computer in a government office. It is a chain. A sensor must survive. The sensor needs power. The data connection must work. The central system must receive the data. Someone must interpret it. The warning must reach local authorities. Then it must reach the public. Finally, the public must act. Break any link and the system becomes weaker. March 11th damaged several links at once. Fact number 83. The tsunami reached Hawaii and the west coast of North America hours after Japan was struck. The catastrophe was local in destruction, but ocean-wide in reach. Once generated, the tsunami spread across the Pacific Basin. In deep water, tsunami waves can travel at the speed of a jet aircraft, while remaining relatively low compared with the towering waves they can become near shore. Hawaii began seeing the tsunami roughly 8 hours after the earthquake. The west coast of the United States saw it later, around 9 to 10 hours after the main shock, depending on location. Those hours created a very different kind of emergency from the one in Japan. There was time to issue warnings. Harbors could be cleared, coastal residents could move, officials could watch instruments and estimate arrival times. But distance did not make the wave harmless. Strong currents damaged harbors and boats around the Pacific. In California, the tsunami caused serious damage in places such as Crescent City, where harbor geometry can amplify incoming energy. Tsunami warnings, therefore, cannot be based only on whether someone expects a dramatic wall of water. A sea level change that looks modest offshore can produce dangerous currents inside a harbor. Water may surge in and out repeatedly. Boats can be torn from moorings, docks can break apart, and the Pacific did not stop carrying evidence of the disaster after the waves were gone. For years, objects that had been pulled out of Japanese towns continued drifting across the ocean. Some were small enough to pick up by hand. Fact number 84. Pieces of Japan continued arriving on North American shores years after the tsunami. The wave did not only move water, it carried houses, fishing gear, boats, wood, containers, plastic, vehicles, sections of docks, and countless smaller objects into the Pacific. Japan estimated that about 5 million tons of debris entered the ocean during the tsunami. Much of it sank relatively close to shore, but an estimated 1.5 million tons remained floating long enough to disperse into the Pacific. Then, ocean currents and winds took over. Months later, debris began appearing around the Pacific. Some pieces could never be conclusively linked to the tsunami. Others carried serial numbers, registration marks, names, or other details that allowed investigators to trace them directly back to Japan. A remarkable example was a massive concrete dock from the port of Misawa. A dock weighing roughly 185 tons crossed the ocean and later reached the coast of Washington state. Another Japanese dock reached Oregon. Boats, buoys, a motorcycle, sports balls, and other recognizable objects were also confirmed as tsunami debris. Some items carried living passengers of a different kind. Marine organisms from Japanese coastal waters survived the journey attached to floating debris, raising concern about non-native species reaching North American ecosystems. The tsunami had ended in Japan within hours. Its debris kept telling the story for years. Fact number 85. The Japanese tsunami broke icebergs off Antarctica. This sounds like a detail invented to make the disaster seem larger. It is real. After the earthquake, scientists followed the tsunami as it moved across the Pacific and eventually reached Antarctica about 18 hours later. By then, the waves at the Sulzberger ice shelf were only around 30 centimeters high, roughly 1 foot. That does not sound threatening. But an ice shelf is a huge floating sheet attached to the coast, and a tsunami is not an ordinary short wind wave. The repeated long-period motion flexed the ice. Satellite images showed that several icebergs broke away after the tsunami arrived. Together, the pieces covered roughly 125 square kilometers, close to 50 square miles. The section of ice had remained intact for at least several decades before that event. The National Aeronautics and Space Administration described it as the first direct observation of a tsunami triggering this kind of iceberg calving. The fact is useful because it corrects the mental picture of a tsunami as a local splash that fades after it leaves a beach. The energy spread through an entire ocean basin. It moved boats in California. It triggered warnings around the Pacific. It crossed more than 13,000 kilometers to Antarctica and flexed floating ice strongly enough to break pieces free. Fact number 86. The tsunami left salt behind on farmland that had fed communities for generations. When seawater floods a city street, the visible damage is obvious. When it floods a field, some of the worst damage can remain after the surface looks dry. Salt water entered large areas of agricultural land along the Tohoku coast. It deposited salt, mud, debris, and in some places, contaminants or oil. Drainage systems were damaged. The ground itself had subsided in parts of the coast, making some fields more vulnerable to future flooding. Farmers could not simply wait for spring and plant as usual. Recovery required clearing debris, restoring drainage, washing salt from soil, repairing irrigation, rebuilding farm roads, and sometimes changing the shape or elevation of fields. The scale was enormous. Nearly 20,000 hectares of tsunami-affected farmland were eventually included in recovery measurements used by Japan's Reconstruction Agency. By the early 2020s, farming had resumed on roughly 95% of the farmland counted in that recovery program, excluding land converted to other uses. That number represents years of work hidden behind a simple green field. Agricultural recovery also faced a problem that engineering could not solve by itself: trust. After the Fukushima accident, Food from Fukushima and surrounding areas faced public concern about radiation. Japan expanded testing and monitoring of agricultural products, while producers struggled with reputational damage even when products met safety standards. So the recovery of a field involved two battles. First, make the land productive again. Fact number 87. For fishing towns, rebuilding the port was only the beginning. The northeastern coast of Japan is deeply connected to the sea. Fishing is not just a job performed on boats, it is an entire network. Boats need docks and fuel. Catch must be landed, sorted, refrigerated, processed, transported, auctioned, and sold. Ice plants, warehouses, roads, markets, repair yards, and factories all support the industry. The tsunami attacked every part of that chain. Fishing vessels were sunk or carried inland. Ports were filled with debris. Processing plants were destroyed. Refrigeration was lost when power failed. Coastal communities lost workers and customers at the same time. Then Fukushima added another challenge. Fishing in some areas was restricted or reduced, while authorities monitored radioactive materials in seawater and seafood. Even where products passed testing, consumer fear could remain. Recovery, therefore, took years and varied greatly from place to place. Ports were rebuilt, boats returned, markets reopened, processing facilities came back. Monitoring programs tested seafood, and restrictions were adjusted as conditions changed. But the industry also had to deal with something harder to rebuild than concrete: population. Young people who had moved away during the disaster did not always return. Some older workers retired. A town could rebuild a perfect harbor and still have fewer people available to operate the businesses around it. Reconstruction statistics can mislead if they are read too quickly. A bridge can be 100% rebuilt. A human community cannot be measured so neatly. Fact number 88. Japan created a special reconstruction agency to act as a control tower for the recovery. The Reconstruction Agency did not exist on March 11th. It was created in February of 2012, almost a year after the disaster. Its job was to coordinate the enormous reconstruction effort across national ministries and local governments. Japan itself describes the agency as a control tower for reconstruction. That phrase makes sense when you look at the problems involved. One ministry might be responsible for roads, another for agriculture, another for housing, another for nuclear policy. Local governments needed money and approvals. Towns needed land plans. Railways, ports, schools, hospitals, and businesses all had different schedules. Without coordination, one project could easily wait for another. A new residential area might need a road before houses could be occupied. A fishing port might reopen before nearby processing plants were ready. A railway could be repaired through a town whose residents had not yet decided where the new town center would be. The agency was designed to push those pieces together. Originally, the central reconstruction period was expected to last about a decade, but the work, especially in Fukushima, proved longer. The agency's life was extended into the current decade. Rescue and reconstruction run on very different clocks. Rescue is measured in minutes and days. Reconstruction is measured in years and sometimes generations. Fact number 89. Japan committed tens of trillions of yen to reconstruction. The physical destruction alone made the Great East Japan earthquake the costliest natural disaster ever recorded in economic terms at the time. But direct damage was only the beginning. Japan then had to finance housing, roads, railways, ports, seawalls, schools, land raising, decontamination, business support, debris removal, nuclear decommissioning, and assistance to displaced residents. During the first 5-year intensive reconstruction period, the government allocated about 25 trillion yen for reconstruction efforts. A further roughly 6.5 trillion yen was allocated for the following 5-year reconstruction and revitalization period. Those numbers are so large that they are almost meaningless until you picture what they paid for. A new hillside neighborhood requires excavation and utilities. A destroyed railway may need a new alignment. A harbor needs breakwaters and cranes. Debris has to be sorted and disposed of. Public housing has to be built. Roads must be elevated. Schools need to reopen. Farmers need fields restored. Businesses need customers. Then, Fukushima added costs that do not exist after an ordinary earthquake: decontamination, long-term storage, monitoring, compensation, and a decommissioning project expected to continue for decades. Money can rebuild infrastructure, but it cannot make every former resident return. In Fukushima, rebuilding a place and rebuilding a population turned out to be two different jobs. Fact number 90. Parts of Fukushima remained difficult to return to long after most of the prefecture was open. The word Fukushima became internationally associated with the nuclear accident, but Fukushima is a large prefecture. Most of it was never an exclusion zone. The restricted areas were concentrated around Fukushima Daiichi and locations affected by radioactive contamination. Over time, extensive decontamination and infrastructure work allowed evacuation orders to be lifted across many communities. Roads reopened, rail service returned. Shops, schools, medical facilities, and housing were rebuilt. By the early 2020s, the land covered by evacuation-designated zones had fallen from roughly 12% of Fukushima Prefecture after the accident to only a few percent. But a few percent on a map can still represent real neighborhoods. Within the most contaminated locations, areas classified as difficult to return required a slower process. Japan created special reconstruction bases where decontamination and infrastructure work could be concentrated, so residents could return to selected areas first. By November of 2023, evacuation orders had been lifted in all 6 municipalities' designated reconstruction base areas. That did not mean every former resident came home. Some had spent more than a decade elsewhere. Children had grown up. Families had bought houses in new cities. Jobs had changed. Elderly residents had died. Returning to a reopened street is not the same as returning to the life that existed there before March 11th, and some difficult-to-return zones still remain. The map has shrunk dramatically. Fact number 91. One railway reopening became a quiet milestone in Fukushima's recovery. Railways are easy to overlook in a disaster story because they do not produce dramatic before and after images like a reactor building or a giant seawall. But a railway tells you whether ordinary life is reconnecting. The Joban line runs along Japan's Pacific side and passes through Fukushima. Sections of it were damaged by the earthquake and tsunami, and the nuclear evacuation zone cut the route as well. For years, passengers could not simply ride the entire line through the affected region. Gradually, sections reopened as tracks were repaired, stations rebuilt, and evacuation orders changed. In March of 2020, the Joban line finally resumed service along its full route again. That date came 9 years after the disaster. A train passing through a town is not the same as a town being fully recovered. Some stations served communities with far fewer residents than before. Some neighborhoods nearby were still rebuilding. But transportation creates possibilities. It connects residents to jobs, schools, hospitals, relatives, and businesses. It makes return easier for people who do not drive. It gives visitors access to places that had been physically and psychologically cut off. By the early 2020s, the Reconstruction Agency reported that most public infrastructure damaged by the disaster had been restored. The visible scars were disappearing. Fact number 92. Some damaged buildings were intentionally preserved so future generations could see what the tsunami did. Reconstruction usually means removing ruins. A destroyed building is unsafe, painful to look at, and often sits on land needed for something new. But if every trace of a disaster disappears, the next generation may inherit only numbers in a textbook. Across Tohoku, communities debated whether certain damaged structures should remain as memorials. The decisions were not simple. For survivors, a ruined school or public building could represent the worst day of their lives. Some wanted the structures removed. Others believed the physical evidence was too important to lose. Several disaster ruins were eventually preserved alongside museums and memorial facilities. Visitors can see bent steel, broken concrete, watermarks, damaged classrooms, and the distances between the sea and places that once seemed safe. The purpose is not to make destruction entertaining. It is to make scale understandable. A sign saying the tsunami reached a certain height is information. Standing beside a building and seeing where the water actually reached is different. Japan also developed networks of museums, archives, storytellers, and memorial sites to preserve personal accounts and evacuation lessons. That effort matters because memory weakens naturally. A child born after 2011 can now be a teenager with no personal memory of the disaster. In another few decades, most people living on the coast will know March 11th only through what previous generations chose to preserve. Fact number 93. The disaster turned evacuation education into something as important as concrete defenses. Japan had seawalls before 2011. It had tsunami warnings. It had hazard maps. Japan had built an exceptionally advanced earthquake monitoring system. And still, nearly 20,000 people died or remained missing after the combined disaster. That does not mean the preparations were useless. They saved lives. It means no technical system can remove the need for human action. Kamaishi became a widely discussed example. Schools there had practiced tsunami evacuation and taught students not to depend blindly on a fixed map or a single designated shelter. Students learned to move quickly towards safer ground and to keep moving higher if conditions suggested the first location was not enough. During the disaster, groups of students evacuated as the situation changed. The overwhelming majority of school-aged children in Kamaishi survived. The story is sometimes simplified into a miracle, but the useful part is that it was not magic. It was preparation practiced before the emergency. After the disaster, Japanese education and public safety campaigns placed renewed emphasis on immediate self-evacuation. If you are near the coast and feel strong or long shaking, the earthquake itself may be your warning. Move away from the coast and rivers. Go higher. Do not return because the first wave looks small. Do not wait for someone else to make the decision for you if the danger is obvious. Those instructions sound basic. Fact number 94. The tsunami changed coastlines, but it also changed how scientists study the next great earthquake. The magnitude 9 earthquake was not just a disaster to explain after the fact. It became a giant data set. Seismologists studied the rupture. Geodesists measured how far the land moved. Ocean scientists analyzed tsunami propagation. Engineers inspected buildings, seawalls, bridges, and nuclear systems. Social scientists studied evacuation behavior. Public health researchers followed displaced communities. The findings changed assumptions. Before 2011, some hazard models did not fully account for a rupture of this scale along that section of the Japan Trench. Historical evidence of older giant tsunamis existed, including geological deposits left by waves centuries earlier. But the modern disaster showed how dangerous it can be to base future planning mainly on the relatively short period covered by instruments and written records. Afterward, researchers placed greater emphasis on paleo-tsunami evidence, layers of sand and sediment carried inland by ancient waves. A quiet layer of sand buried beneath a rice field can be a warning from a disaster that happened before modern records existed. The coast itself stores memory. Scientists can dig into the ground, date deposits, map how far old waves traveled inland, and use that information to estimate events that no living person witnessed. For planners, this expands the question from what has happened in the last century to what may have happened over many centuries. March 11th made that longer memory much harder to ignore. Fact number 95. Japan rebuilt its nuclear regulatory system after Fukushima. Before the accident, Japan's nuclear oversight system was criticized for conflicts, fragmented responsibilities, and an industry culture that had not prepared adequately for an extreme multi-unit accident. Fukushima turned those concerns into a national political issue. In September of 2012, Japan established a new Nuclear Regulation Authority as an independent commission under the Ministry of the Environment. New regulatory requirements followed. Nuclear plants had to address more severe natural hazards, long station blackouts, flooding, hydrogen management, emergency power, and accidents affecting multiple units at the same site. Operators could not simply point to the original design and say the plant had met the rules that existed when it was built. Reactors seeking to restart had to pass reviews under the new standards. This contributed to a dramatic change in Japan's electricity system. In the period after Fukushima, the country's nuclear reactors were progressively shut down for inspections and new regulatory reviews. For a time, Japan operated without any commercial nuclear reactor producing electricity. Some reactors later restarted after meeting new requirements and receiving approvals. Others remained offline or were permanently retired. Whatever position someone takes on nuclear power, Fukushima changed the debate. Supporters argued that stronger engineering and regulation could reduce the risk while preserving low-carbon electricity. Critics argued that the consequences of a severe accident were too large to accept. The argument continues. Meanwhile, the plant that started the debate is still being dismantled. And in 2026, engineers are still sending machines into spaces where humans cannot safely work for long. Fact number 96. 15 years later, tiny drones were still exploring the inside of Fukushima Daiichi. By this point, the timeline becomes almost difficult to believe. The accident happened in 2011. By 2026, decommissioning had advanced enormously, but the most difficult work was still underway. Inside the damaged reactors, melted nuclear fuel mixed with structural materials and solidified into material known as fuel debris. Removing that debris is one of the central challenges of decommissioning. The radiation environment and physical damage make ordinary human inspection impossible in many areas, so engineers use remote technology. Tokyo Electric Power Company has sent robots, cameras, sensors, and drones into the damaged structures to understand what is inside. In 2026, micro-drones were used for investigations inside the primary containment vessel of Unit 3, including areas around the pedestal beneath the reactor pressure vessel. The image is almost science fiction. Machines small enough to fly through damaged nuclear containment spaces, carrying cameras into a reactor that was torn apart by a hydrogen explosion 15 years earlier. But the purpose is very practical. Before engineers can remove large amounts of fuel debris, they need to know its location, shape, surrounding structures, radiation conditions, and possible access routes. Even a small sample can provide valuable information about what the melted material is made of and how it behaves. The slow pace is deliberate. The problem is not simply lifting material out of a hole. Every successful inspection replaces part of the unknown with something engineers can actually design around. Fact number 97. Fukushima's decommissioning has already entered the fuel debris retrieval phase, but only in tiny steps. For years after the accident, the priority was stabilization. Keep the reactors cool, control contaminated water, remove fuel from spent fuel pools where possible, reduce radiation risks around the site, build systems that could operate reliably for years. Only after that foundation could engineers begin the next challenge, retrieving melted fuel debris from inside the damaged reactors. Trial retrieval at Unit 2 marked an important transition. The quantities involved at first were extremely small. That was deliberate. A tiny sample can be removed, packaged, transported, and analyzed. Scientists can learn its composition and physical properties. Engineers can test whether the retrieval equipment works as expected. Each step provides information for designing larger operations. By 2026, Tokyo Electric Power Company was still developing and preparing robotic systems for further investigations and retrieval work. That pace can look frustrating from the outside. 15 years seems like a long time. But the interior of a melted reactor is not a normal demolition site. Radiation limits electronics and human access. Structures may be deformed. Water levels matter. Cutting or moving material can create dust. Every operation must avoid creating a new path for radioactive material to escape. The safest approach is often to learn a little, redesign, and try again. Fukushima therefore has two clocks. The first clock measured the accident in hours. Power lost, cooling lost, fuel damaged, hydrogen produced, buildings exploded. The second clock measures recovery in decades. Fact number 98. The treated water controversy is part of a much larger water problem created by the accident. Water helped prevent the damaged reactors from becoming even hotter after the accident. Then, water became one of the site's longest-running engineering challenges. Cooling water came into contact with radioactive material. Groundwater also entered damaged buildings. That produced contaminated water that had to be pumped, stored, treated, and managed. Tokyo Electric Power Company built systems to reduce groundwater inflow and remove many radioactive substances from collected water. The treatment system is known as the Advanced Liquid Processing System. Tritium is different. It is a radioactive form of hydrogen and is difficult to remove from large volumes of water using ordinary treatment methods. As storage tanks filled the site, Japan decided to discharge treated and heavily diluted water to the ocean under a multi-year plan. The releases began in August of 2023. The decision was controversial in Japan and abroad, particularly among fishing communities and neighboring countries. The International Atomic Energy Agency conducted a safety review and concluded that the planned approach was consistent with international safety standards and that the radiological impact on people and the environment would be negligible under the assessed plan. The agency also maintained an on-site presence and independent monitoring. That does not mean everyone suddenly agreed with the policy. Technical risk and public trust are different problems. A measurement can be below a safety limit, while a fisherman still worries that customers will stop buying the catch. Fact number 99. Even today, the disaster is remembered in Japan by a date, 3/11. In the United States, people often refer to major events by dates such as 9/11. In Japan, March 11th became 3/11. The shorthand appears in museums, memorial projects, archives, public discussions, and anniversary events. At 2:46 in the afternoon each March 11th, ceremonies and moments of silence mark the time the earthquake began. The date connects events that can otherwise feel like separate stories. The shaking in Tokyo, the wave at Rikuzen Takata, the flooded Sendai airport, the fires in coastal towns, the evacuation around Fukushima, the explosions at the nuclear plant, the shelters, the search teams, the missing families, the years of reconstruction. They all began with the same rupture under the Pacific. The anniversary is also used for disaster education, because memory has a practical purpose in a country that will face major earthquakes again. Japan sits along active plate boundaries. Another destructive earthquake is not a strange possibility. It is part of the country's long-term reality. For that reason, warning drills, evacuation routes, hazard maps, emergency supplies, and public education remain part of ordinary life. The most useful memorial is not fear. It is remembering what actions gave people a better chance of surviving. And that brings us to the final fact, because the story of March 11th is not finished by saying Japan rebuilt. The more accurate ending is that Japan rebuilt differently. Fact number 100. Japan kept the National Reconstruction Agency in operation beyond the original 10-year recovery period because the disaster did not end on the same timetable everywhere. The agency was created in February of 2012 to coordinate rebuilding after the earthquake, tsunami, and nuclear accident. At first, the central reconstruction period was expected to last about 10 years. That sounded generous in the months after the disaster. 10 years later, the reason it was not enough was obvious. Much of the physical rebuilding in Iwate and Miyagi had advanced dramatically. Roads, railways, ports, housing, and public buildings had returned. Some towns had moved residential districts to higher ground. New seawalls and evacuation routes had changed the coastline. Fukushima was different. Decommissioning the damaged nuclear plant was still measured in decades. Some former evacuation areas still required long-term work. Communities had to rebuild populations and local economies after residents had spent years living somewhere else. Removing fuel debris from the damaged reactors was only beginning in small, carefully controlled steps. The Japanese government therefore continued the reconstruction agency through fiscal 2030. By 2026, the government had already entered a third reconstruction and revitalization period, covering another 5 years of work. That makes the final fact unusually concrete. A government agency created because of one afternoon in March 2011 is still operating 15 years later, and it is expected to remain part of the recovery almost 2 decades after the earthquake. That is where the 100 facts end. The most useful way to remember March 11th is not as a single image of a wave or a damaged reactor. It is as a sequence of problems arriving faster than people could solve the previous one. The earthquake warning bought seconds. The tsunami warning bought minutes. In many places, those minutes were enough for people who moved immediately. In other places, the first estimates sounded less dangerous than the water that was actually coming. Japan changed its systems afterward because the disaster showed exactly where the assumptions had failed. Tsunami warnings were redesigned for earthquakes so large that their true size may not be clear in the first minutes. Coastal defenses were rebuilt as layers rather than as a promise that one wall could stop everything. More communities moved homes to higher ground. Nuclear regulations were tightened around flooding, long power losses, hydrogen, severe accidents, and several reactors failing at the same time. And one lesson needs almost no technical knowledge at all. If you are near the coast and feel very strong shaking, or shaking that lasts unusually long, the earthquake itself may be your first tsunami warning. Do not wait on the beach for a perfect number. Move inland and higher, and stay away until authorities say the danger has passed. On March 11, 2011, some people had only minutes to make that decision. Much of what Japan rebuilt afterward was designed to give the next person a better chance to use those minutes well.